Hello students, good morning. You are welcome in the lecture number 4 of a chapter of Ionic Equilibrium. In the third lecture, we have seen Lewis's theory of acid and base, followed by classification of acid and base, and finally the dissociation constant of weak acid and weak base. Now here we have to study Oswald's dilution law. Oswald's dilution law for weak acid and weak base. First one, we are studying the Oswald dilution law for weak acid. We know weak acids are the substances which will undergo incomplete dissociation. They are producing less number of H plus ions. They are undergoing reversible dissociation, partial dissociation or reversible dissociation. Both forward as well as backward reaction is possible for the weak acids. So HA, let us consider the weak acid HA undergoing incomplete dissociation, reversible dissociation, producing H plus and A minus ions. This undergo incomplete dissociation, producing H plus and A minus ions. Since it is weak acid, this will undergo partial dissociation. Further, forward reaction as well as backward reaction is possible. Dissociation as well as association is possible at equilibrium. Therefore, it is known as weak acid. Now, let us consider the moles. Moles at start, that is initial moles. During any chemical reaction, only reactant is present at start and products are absent. So let us start with 1 mole of the reactant we have taken, 1 mole of weak acid we have taken at start. So initial mole is 1, this is 0, this is also 0. Then the equilibrium take place, moles at equilibrium. Let us consider out of 1 mole, alpha moles undergo dissociation. So what is the moles of HA left behind at equilibrium? Are you getting it? See here. Suppose we have started with HA giving H plus and A minus ions. If we have 10 moles, at start. This is 0, this is also 0. Out of 10 mole, if 2 moles are dissociated at equilibrium, how many moles of HA will left behind? 10 minus 2, that is nothing but 8. So this will be 8. How many H plus ions are obtained? 2. How many A minus ions are obtained? 2. Are you getting it? We have started with 10 moles. Out of 10 moles at equilibrium, 2 moles are dissociated. So 2 H plus and 2 A minus are obtained. And how many left behind? 10 minus 2, that is 8. Instead of this data, we are considering 1 mole present at start of the reaction. Out of 1 mole, alpha moles are dissociated. Therefore, H plus ions obtained is alpha, A minus ions obtained is also alpha, and the moles of HA left behind will be 1 minus alpha. Now what is concentration? If we consider the total volume concentration at equilibrium by considering total volume as P liters. What is concentration? Concentration is nothing but the number of moles present in the total volume. So total volume is V liter. concentration of HA at equilibrium will be there for 1 minus alpha upon V. Concentration of H plus ion is alpha upon V, and concentration of A minus ions is also alpha upon V. This is the only important data. Once if we know this data, how to put it, we can easily obtain the relation according to Oswald dilution law. The next part is very simple. Oswald dilution law, obtain the expression according to that law is very simple once we know this data. So let us see it once again. Let us consider 1 mole of weak acid initially taken. Only reactant is present at start. So products H plus and A minus are 0 and 0. At equilibrium, number of moles of HA will be 1 minus alpha. That of H plus is alpha, A minus is alpha, because out of 1 mole, alpha moles will undergo dissociation. Concentration is nothing but a ratio of number of moles present in given hollow. So at equilibrium, the concentration of weak acid is 1 minus alpha upon V. That of H plus is alpha upon V. A minus is also alpha upon V. Once if we know this data, we can easily obtain the expression for Oswald dilution law. Now see that expression. For this reaction, we know the dissociation constant. Since it is acid, dissociation constant Ka will be equal to concentration of H plus ion into concentration of A minus ion divided by concentration of Ha. So substitute these values: H plus ion concentration, A minus ion concentration, and Ha concentration. Substituting in this equation, what we can write? Ka is equal to H plus alpha upon V multiplied by, see, H plus will be alpha upon V multiplied by A minus, that is also alpha upon V, divided by concentration of HA, it is 1 minus alpha upon V. 1 minus alpha divided by V. Cancel the similar terms from numerator and denominator. One of the volume from numerator and denominator is cancelled. The equation will be Ka is equal to alpha square divided by V into 1 minus alpha. Here alpha square, this is alpha into alpha square. Or we will increase one more step if you have any problem. It is alpha square divided by V multiplied by 1 upon 1 minus alpha. This I have inverted. So Ka will be equal to alpha square divided by V into 1 minus alpha. Now, if the electrolyte, if the acid is very weak acid, if acid is very weak acid, at that time alpha is very less. Alpha is in the order of 10 raised to minus 5. So 1 minus alpha will be equal to 1. Therefore 1 minus alpha will be equal to 1, because alpha is very small and the acid is very weak acid. Therefore 1 minus alpha will be equal to 1, and this equation becomes Ka will be equal to alpha square divided by V. Since volume and concentration are inversely proportional to each other, with increasing volume concentration decreases, or with decreasing volume concentration increases. So 1 upon V is nothing but concentration. This equation can also be written like this: Ka will be equal to alpha square into C. Let this is equation number 2. From equation 1, What is alpha square? Alpha square will be equal to Ka into V. Therefore, alpha is equal to square root of Ka multiplied by V. From this equation, alpha square will be equal to Ka upon C. Therefore, alpha is equal to square root of Ka upon C. Here, alpha is degree of dissociation. Ka is dissociation constant of acid. V is volume of solution. Similarly, from this equation also, here also alpha is degree of dissociation. Ka is dissociation constant of acid and C is concentration of acid. So, from this equation, what is the Oswald dilution law? See, Oswald dilution law is mathematical law. It is a mathematical law. Where from this equation, it is stated that degree of dissociation alpha is directly proportional to square root of dissociation constant as well as directly proportional to square root of volume dilution. Volume means dilution. Degree of dissociation alpha is directly proportional to dissociation constant as well as directly proportional to square root of dilution. According to this equation, Oswald dilution law can be stated as degree of dissociation is directly proportional to square root of dissociation constant and inversely proportional to square root of concentration. That is the Oswald dilution law for weak acid. Now let us see Oswald dilution law for weak base. Very simple. Weak acid replaced by weak base. We know instead of Ha, now consider the weak base BOH. This is partially dissociated, giving B plus OH minus. Now second, Oswald dilution law for weak base. So let us consider the weak base BOH undergoing reversible, partial, incomplete dissociation, giving B plus and OH minus ions. Reversible. At equilibrium, both forward as well as backward reaction are present. At the state of dynamic equilibrium, reaction is not stopped. Concentrations are constant. Concentration of BOH, B plus and OH minus. Concentrations are constant at equilibrium, but reaction is not stopped. That is the state of dynamic equilibrium. So let us consider 1 mole of the weak base BOH initially taken. At that time, the initial mole of B plus is 0, OH minus is also 0. Same equation we have to use, same as that of the weak acid. Similar type of expression is there. Initially 1 mole of BOH, weak base is taken, this is 0, this is also 0. At equilibrium, out of 1 mole, if alpha moles undergo dissociation, then moles at equilibrium of weak base is 1 minus alpha, B plus is alpha, OH minus ion is also alpha. Concentration at equilibrium is nothing but the ratio of number of moles to the total volume. Total volume we have considered as B liters for weak acid. For weak base also let us consider the same volume V liters. So concentration at equilibrium BOH 1 minus alpha upon V, B plus alpha upon V, OH minus also alpha upon V. Now instead of Ka, here it is Kb. Dissociation constant of base is Kb. Instead of this equation, here apply the law of mass action for this equilibria and we will get this equation B plus into OH minus divided by concentration of BOH. Substituting for B plus OH minus and BOH, these values, similar type of substitution is there. Only Ka will become Kb. Ka will become Kb. Remaining part is same. B plus is alpha upon V. Then OH minus, that is also alpha upon V. Concentration of BOH 1 minus alpha upon V. So substitution is same. Cancelling one of the volume term from denominator and numerator, will get the same equation. Alpha square upon V multiplied by 1 upon 1 minus alpha. Similar one, alpha square upon V into 1 minus alpha. Since weak acid has very less degree of dissociation, in the similar manner for weak bases also have a very less degree of dissociation. Alpha is equal to 10 raised to 5 or even less than that also. At that time 1 minus alpha will become equal to alpha, and this equation we can write as Kb is equal to alpha square upon V. Since concentration and volume are inversely proportional to each other, this we can write Kb will be equal to alpha square C. So here also every time Ka is replaced by Kb, and finally we will get the equation for Oswald dilution law for weak base. Only Ka we are replacing by Kb. We are replacing Ka by Kb, and we are replacing the weak acid Ha by BOH. Almost the total expression is same. Here also dissociation constant can be explained, which is depending on the degree of dissociation by this equation. Here Oswald dilution law can be stated as degree of dissociation is directly proportional to square root of dissociation constant as well as directly proportional to square root of volume. According to this equation, degree of dissociation is directly proportional to square root of dissociation constant, but inversely proportional to square root of concentration. So that is there about the Oswald dilution law for weak acid and weak base. See, using this law we have to solve certain problems. They are giving the value of alpha, they are giving the value of concentration, and they are asking to calculate the dissociation constant. Let us see one problem. According to Oswald dilution law, dissociation constant can be calculated, or degree of dissociation can also be calculated. Let us see one numerical example how to calculate the degree of dissociation or dissociation constant. Suppose they have given the weak acid or maybe weak base. Since here we have equation for weak base, I am taking the problem of weak base. Suppose they have given the weak base magnesium hydroxide, MgOH twice. Magnesium hydroxide is weak base, of which degree of dissociation alpha is given. Suppose they have given the alpha 0.06%. This is the percent alpha they have given, and concentration of this magnesium hydroxide, let us consider, that is equal to 0.03 moles per decimeter cube. Molar concentration is given, and they have asked to calculate the dissociation constant of base Kb. In the problem they are giving that the degree of weak base is 0.06% or weak base is 0.06% dissociated in its 0.03 molar concentrated solution, calculate the dissociation constant of base. So Kb we have to calculate. What is the equation for Kb? Kb is equal to alpha square C. We know that equation. Kb will be equal to alpha square multiplied by C. C is concentration, 0.03 molar given. Alpha is degree of dissociation. Alpha is the degree of dissociation. But they have given percent alpha. They have given percent degree of dissociation. Percent alpha is given. So this percent alpha we have to convert into the alpha. Therefore, what is the equation for alpha? We know alpha will be equal to percent alpha divided by 100, because whenever alpha is multiplied by 100, we will get the percent alpha. Therefore, alpha is equal to percent alpha divided by 100. So, calculating alpha, that is percent alpha upon 100. Percent alpha is 0.06%. It is the 0.06 divided by 100. So alpha will be equal to 0.0006, or that is also written like this: 6 into 10 raised to minus 4. This is the alpha. Concentration we know. Now directly substitute in the equation of Kb. Therefore Kb will be equal to alpha square C. Alpha is 6 into 10 raised to minus 4 square. Alpha square, 6 into 10 raised to minus 4 square, into C, that is into concentration 0.03. For sheet, the solution is like this: Kb is equal to this. We are solving 36 into 10 raised to minus 8 multiplied by, this is 3 into 10 raised to minus 2. This is 3 into 10 raised to minus 2. We have written 0.03. Can also be written like this manner. So Kb will be equal to 3 multiplied by 36. 3 6 are 18. 3 3 are 9 plus 1 10. 108 into 10 raised to minus 8 minus 2, that is 10 raised to minus 10, or it is also written like this: 1.08 into 10 raised to minus 8. This is the dissociation constant of weak base. In this manner, if we are given the values of degree of dissociation, that is a percent degree of dissociation, and concentration, if we are given the percent degree of dissociation and concentration, we can calculate the dissociation constant of base in this manner. Let us see it once again. The degree of dissociation in percentage is given as 0.06%. Of that weak base, concentration is 0.03 molar, and we have to calculate the dissociation constant of base. Dissociation constant of base, according to Oswald dilution law, has this equation: alpha square C. Kb is equal to alpha square C, where this alpha is degree of dissociation. It is not a percent degree. It is simply a degree of dissociation alpha. So alpha will be equal to percent alpha divided by 100. Percent alpha is given as alpha is equal to 0.06 upon 100. That is equal to 0.0006, or 6 into 10 raised to minus 4. So Kb is equal to, substituting this value, 6 into 10 raised to minus 4 square into concentration 0.03, solving this bracket, 36 into 10 raised to minus 8, this is 3 into 10 raised to minus 2, multiplying 36 by 3, we will get 3 6 are 18, so 8, then 3 3 are 9 plus 1 10, 108 into 10 raised to minus 10. This can also be written in this format, 1.08 into 10 raised to minus 8. This is the dissociation constant of that given weak base magnesium hydroxide. Now let us see one more example which they have given in the form of solution in your book. Let us consider the other case, weak base which has a concentration of 0.02 molar and percent alpha is given as 0.05% dissociated. Weak base is 0.05% dissociated in its 0.02 molar solution, and calculate the dissociation constant of such a type of weak base. You got the problem? What they are asking? They are asking to calculate the dissociation constant of weak base. Here they have given the percent alpha 0.05% and the concentration of base is 0.02 molar. We have to calculate Kb. Again in the similar manner, we know the equation Kb is equal to alpha square C, where this alpha is a degree of dissociation. It is not a percent degree of dissociation. Since we know percent alpha will be equal to alpha into 100, therefore from that equation alpha will be percent alpha divided by 100. Very simple. Degree of dissociation alpha is a fraction. It is a fraction of total moles of an electrolyte which have undergone dissociation. The fraction of total moles of an electrolyte which have undergone dissociation is known as degree of dissociation. If this is multiplied by 100, we will get the percent degree of dissociation. So percent degree of dissociation is degree of dissociation into 100. So alpha, degree of dissociation will be percent alpha divided by 100. Substituting the value of alpha, percent alpha, we will get alpha is equal to percent alpha 0.05 divided by 100, that is equal to 0.0005, or alpha is written as 5 into 10 raised to minus 4. This is the alpha, and this alpha we can use now to calculate the dissociation constant. So substituting there, Kb will be equal to alpha square C. Alpha is now 5 into 10 raised to minus 4. 5 multiplied by 10 raised to minus 4 square, alpha square, into C into concentration, that is 0.02 molar. Solving this in the similar manner as that of the previous problem. So we can write Kb is equal to 25 multiplied by 10 raised to minus 8 into, it is written as 2 into 10 raised to minus 2. So Kb 25 into 2, 50, multiplied by 10 raised to minus 10. So Kb is equal to 5 into 1 decimal I have taken on left side. So minus 9. 5 into 10 raised to minus 9 is the dissociation constant of this weak base. So how to solve this type of problem? If we are given the concentration of base, we are given the percent alpha, and we are asked to calculate the dissociation constant. At that time we know this equation. This is the equation according to Oswald's dilution law. Oswald's dilution law for weak base. Kb is equal to alpha square c, where this alpha is degree of dissociation. It is not a percent degree. We know percent degree of dissociation is alpha into 100. Therefore alpha is equal to percent alpha divided by 100. So alpha is equal to percent alpha is 0.05 divided by 100. That is 0.005. This is also written like this: 5 into 10 raised to minus 4. Substituting this value in this equation, Kb is equal to 5 into 10 raised to minus 4 square into concentration 0.02 molar. This is 25. Square of 5 is 25 into 10 raised to minus 8. This is written as 2 into 10 raised to minus 2. 25 into 2 it is 50 into 10 raised to minus 10. So instead of this format we can write like this: 5 into 10 raised to minus 9. That is the dissociation constant of weak base. In that manner, the dissociation constant of weak base can be solved, or the dissociation constant of weak acid can also be calculated using this type of equation according to Oswald dilution law. If we know the value of percent alpha and concentration. So here we have completed the Oswald dilution law for weak acid, Oswald dilution law for weak base, and numerical examples also we have completed on the basis of Oswald dilution law.